Really start today, so I'm able to do a more in-depth discussion. Uh, well, as best as I can. Okay, so let me just get my notes and then continue with the lecture. So, the lectures on this theory is a bit spitfire because again we're still working on the course outline, and this is a relatively new field of study in our curriculum. So yeah, there's that. So let me just catch my breath. I run a mile. Okay, so just need to expound on the group and the group axioms. So I found a better whiteboard marker. I hope you guys can see that. Yeah. So we discussed that a group is a mathematical structure that is that satisfies some certain properties. That it's a set. Let's see, n, equipped with some operator, which I'll call asterisk, which is some operation that maps n tuples of n onto n. So it takes in one or two more elements, does something to them, and then that thing over there. And so I want to say that the operation over to AB in n is also an element of n. That's what it means to have closure. So the result of applying this asterisk onto elements A, B, suppose addition, is inside n. So the sum A plus B is inside n. So that's that. Now here's some additional things that groups need to satisfy. I already stated that every element inside n must have an inverse for the operation. So if it's some group equipped with the addition operator, then every element must have a negative counterpart. So it needs to have an inverse, right? Such that if we add them both together, we would get the identity element. So in this case, if we add two inverses, so in a number in its inverse, then we would get 0, the additive identity. So this actually defines subtraction. So 0 is the identity, additive. It's the additive identity. So it checks out. And so stuff like the integers, equipped with the addition operator forms an additive group. So yeah, that's just a fancy way of saying that it's a group, or it's a group that's closed under addition. And so does Z times the multiplication operation. This also forms a group, I believe. Actually, no, it's not that. It's R. I'm sorry, I mean R, or rationals. R equipped with the multiplication product, which would take two or more inputs, would be a multiplicative group. Because the rationals, like 1 over A, which is part of the rational numbers, is the rational numbers are a subset of R. But the thing is, the rational numbers on its own, equipped with the multiplication operator, will not form a multiplicative group, because if we take the inverse of 1 over a, we would get just a, because that's just 1 over 1 over a. And you guys need to know that this just cancels out, and then we're just left with a, which is not a part of q, but rather a part of z. And there's an element of z. Which is why it's not close then. So yeah, because it doesn't have inverses, I mean, it doesn't follow that in the inverse axiom, or one of the group axioms. Now, here's another thing, another assumption for group axioms. So I'll just list it down here. So of course, for a group G equals n with some operation dot, which we will say the multiplication operation, and elements A, B, and C in G. First axiom that a group must satisfy is that for all AB inside G, the group A times B inside the parentheses times C is equal to A times parenthesis B times C close. So what this first axiom is saying that we can shift this, or it's associative. So if we have 3 elements inside here, and then we multiply 2 things first, and then multiply the third thing, it's the same as multiplying the third thing with the second thing first, and then doing the first thing. Okay. So the second one, the second axiom, is that, our additive inverse. For all A inside G, there exists an identity element E such that A times E is equal to E times A, which is equal to A. So in the case of the integers, and or rather the real numbers, and then equipping it with the multiplication operation, our multiplicative inverse here is actually just 1, because A times 1 is just A, or any number times 1 is just that number. So a group must have this. So let's say a group which is, let's try to make a structure which is, say, the integers without number 0, equipped with the addition operation. Does this form a group or not? Of course it doesn't, because in the case of addition, our additive identity is 0, and since we remove 0, extract the 0 from Z, or the integers, that means we don't have an additive inverse anymore, so it doesn't follow the group axioms. So this is not a good thing. So this is not a group, or it doesn't form a group under addition. Okay. But if 0 is part of the integers, or if we just use the regular form of the integers without extracting anything, we do form a group under addition. Okay, so the third axiom is that okay, so for all A inside G, there exists an A to the minus 1, or inverse A, such that A by A to the minus 1 is equal to B to the minus 1 by A is equal to E. So we get our multiplicative or additive inverse if we have our thing here. So in the case of equipping our set with addition, if we add the two inverses, or as I said, well, if we add the inverse, the number in its inverse, we would get our additive identity, which is 0. And if it's multiplication, if we multiply a by its inverse, which is basically just dividing a with itself, we would get the multiplicative identity, which is 1. So that's that. But the thing is, in abstract algebra, this statement is not necessarily true in some cases. So if you have something like a times b, sometimes there are those cases wherein it's not the same as b times a. Because examine here this expression, xy. Yeah, it's the same here, right? But the thing is, if we swap them to get yx, it's not the same thing. It's not necessarily the same thing. Because someone can construct a mathematical structure wherein this property does not hold, okay? So the neat thing about mathematical structures is that if we want to prove something that's utterly false, like I say 1 plus 1 equals 3, we can definitely do that. So let's see, I want to define this nonsense over here. 1 plus 1 equals 3. Common sense tells us that no, it's 2. It's supposed to be 2, right? But the thing is, I can make a structure or a building wherein this holds. So I can make a set, say, psi, which is composed of 1 and 3. And then I'll equip that psi with an addition operation, such that 1 plus 1 equals 3. Okay? Or rather, yeah, 1 plus 1 equals 3. So now we don't use a or b or any variables here because these are our only elements in the set. So this is actually closed because the only definition for this addition operation is 1 plus 1 equals 3. 3 plus 1 is not defined. So you cannot disprove that this is not closed. It's closed by our definition of addition over this structure. So anyone can write about in any way, prove something that's very, very false by simply creating their own building, right? Their own mathematical structure such that it's true and that it's the only thing that is true so that it cannot be disproved, right? So, but the thing is, don't like immediately start using this to, fight with your teacher, okay? Because the majority of mathematics that teachers talk about, like in calculus or in algebra or high school algebra, high school stuff happens in R, equipped with the addition operation, or R, equipped with the multiplication operation, or R, equipped with the eversion. Or it's just simply something called a ring. R equipped with addition and multiplication. It's just the same as this, but we're just multiplied by inverses. Yeah, it happens here. And the thing is, these guys are governed with specific rules, okay? So if you try to define this, or if you try to say, 1 plus 1 is 3 according to what Professor Femmy said, that's not true, okay? It's not true when it comes to this, okay? Don't fight with your teachers when they say that 1 plus 1 is 2. It's obvious, right? You can say that, you can say by my previous mathematical structure, or you can generalize and say that, according to Professor Femmy, I can construct a structure and then generalize it, right? And then say, a plus a equals 3. So anything else can be 3 now. So 4 plus 4 equals 3 and then stuff. And then you try to fallaciously or surreptitiously apply it here in your system that your school uses, or the majority of mathematics uses. Don't do that, okay? The rule that 1 plus 1 equals 3 is intrinsically belonging to this structure alone, okay? It can only be applied on the structure because that's the only definition we have on the structure, okay? And likewise, as I said, you cannot disprove my definition a while ago. It's a definition, not a theorem after all. It's a fundamental assumption for this mathematical structure. And the thing is, don't clash with your teachers, okay? Just because I said that, well, you can define or make a mathematical structure such that what they said is false, right? Don't do that. It's just for the sake of mathematical playfulness, okay? Don't argue with your teachers. I know you guys are already mature enough to know that, okay? Alright, so that's the group axioms. So there are actually different types of groups, but one of the most common ones, or the most well-known ones, is called the abelian group or abelian group. The abelian group or abelian group. I call it abelian. An abelian group, as I stated in the previous lecture, is a group such that for all AB inside G, well, I'll say that G is composed of some set N equipped with some operator asterisk, such that for all AB inside G, A at asterisk B is equal to B asterisk A. So if we do an operation over two elements part of the set, swapping the elements has no effect. It's the same thing. So that's an abelian group. Again, people pronounce it abelian, I don't know why. The original name of the person who it was named after was Abel, after all. It's pronounced Abel, so what's that? Now, how do these things apply in our theory of femboys? Well, the thing is, what we can do is, well, we can prove certain contradictions like the Banach-Tarski paradox or the first 3 videos of this playlist because we treat them as groups. So in position theory, what we did was express these people as, as either vectors, right? Vectors, V, that's an element of a vector space. Or we can treat them as sets of characteristics, or they are certain points in a topological space, which was our O cross P, topological space, an element of a topological space. So it's not only that, but it's equipped with its topology as well. Yeah. So something as part of a topological space or a point at the in the topological space or element of topological space. But we never actually considered something like groups. So we have a set of characteristics, say masculine and dominant, and then we never really considered about equipping it with something. So treating femboys as their own building, you would say. And because of that, we're able to prove some things like, proving that, well, something is a certain type of femboy is equidecomposable, or it's essentially equal to, well, itself minus one element. So an F is, well, equidecomposable. This is not isomorphic, okay? I don't know why group theorists or, well, abstract algebra, well, people engaged in abstract algebra use this symbol, okay? It's also used to denote isomorphic, so say we have some continuous deformation from this to that, okay? So it's essentially the same, or congruent. Now, there are 3 meanings to this symbol. Congruent in your geometry, or your approximately equal in your algebra. Isomorphic in abstract algebra. And in group theory, we call it isomorphic. And the last one is equidecomposable in general mathematical logic. So if we treated femboys as groups, we can essentially prove that F is equivalent with F minus some element, say the K element. So we can prove that it's the same as this through some contradictions or some splitting. So this is actually done by splitting the group, right, into its various parts and then doing some rotation or some group action on it And then because of that, one of the points or one of the elements disappear. So we think of a circle, right? S1 in abstract algebra. And then we sort of know the center over here called C, right? Or I'll call it O. Okay. And then so we have some ring of points here. And then some circle that connects them all. It passes through the center. And then what we do is just basically apply some rotation here on this set of points. And then so this actually disappears. This center disappears over here. And so it's the same. S1 is the same, or rather equidecomposable with S1 without the center. And then so with some logical stuffs and more application of the axiom of choice, we're able to prove that a unit ball or a solid ball of radius 1 is also equidecomposable with 2 copies of itself. So we're able to duplicate something using the axiom of choice, which is a paradox because we obviously cannot do it in real life. So yeah, very crazy stuff when it comes to groups. But yeah, that's actually the basics of Femboy set theory. We're gonna actually run through the 2 proofs again, or the 3 proofs and the theorems. So yes, that's what. And we can also think of them not only as their own individual buildings, but actually elements of a building. So we can say that F is some, or Femboy is some element of some, well, group of them, right? And then we can add them, have their own inverse, and stuff like that. And all that wonderful stuff. The thing is, when I started proving these things, like, well, say, I also proved that, proved in a previous video that a transgender person is essentially the same as a femboy. And well, because of that, I got a lot of backlash. People kept calling me a transphobic, but it was just in the name of mathematical playfulness. It's just, it has nothing to do with my hatred or anything. I don't hate you guys. And that's how crazy this thing is, or this system is. Mathematical logic in general, abstract algebra. We can come up with very, very wild conclusions and then sort of study them and, well, see what happens from there. Like what we do with it. What the hell do we do with such a contradiction, right? Well, sort of just tuck it at the back of our head, and then it reminds us of how dangerous or powerful or what mathematical logic is. So, yeah. I suppose the next one will start going in depth on a Femboy group, I suppose. I haven't actually constructed it yet, or actually thought about how to construct it. It's just supposed to be a group that satisfies the group axioms, of course. And, yep. Perhaps also talk about subgroups and stuff like that. So, there are actually also different types of groups. There's also something called a Lie group. And yeah, this is very interesting because the field of abstract algebra is very interesting because there's many things or many buildings you can construct with their own special properties. There's even a building or a mathematical structure such that the expression 0 divided by 0 is defined. Well, your high school stuff will tell you, oh well, this is nonsense. This does not make any sense. It's some indeterminate form as dictated in calculus. But there's actually a mathematical structure called a wheel, such that this is defined. This is a thing that exists, and it's something. It's a structure that's this. So W a set, 0, 1, the addition operation, this, and then our inversion. And this is a wheel. And within this structure, this is defined. And so is, well, so is something like A divided by 0. Usually, your teachers would think that, oh, this is just infinity. Or it's something that's undefined, or, yeah. But here, in our case, we define infinity as something that's a definite value, because what we do in your usual mathematics, you have a straight line, right? A straight ray that goes from minus infinity to positive infinity. And then we have some midpoint here, 0, or our origin, right? And then we have our 1, 2, 3, 4, or any number you can think of. What we do with the wheel is that we take this infinity and this infinity, and then we close them together such that minus infinity is equal to positive infinity. And so instead, now, since we have one definite value and turn this into some sort of circle, 0 and then some infinity equals minus infinity, this becomes something called the nullity. Okay? So stuff like this, so a over 0 or 0 over 0 is equal to something called the nullity, which is denoted by this perp sign used in geometry. I don't know why. So yeah, this is a wheel, and so we turn this into something like this, so that infinity divided by infinity is defined. Okay, but this kind of algebra or this kind of mathematical structure is a bit wacky because its algebraic properties is quite wacky, because something like, well, this a this inversion is not the same as an inverse. So it's not the same as a to the minus 1 or 1 over a. It's not the same as that. That's the thing. Even though, well, b divided by a is, well, you would think that this is actually b over a, but that's not necessarily the case with this algebra. And there's some more wacky things. I suggest you guys, well, study that. There's a Wikipedia page. I think I'm gonna link it in the description below. So in general, mathematical structures are very interesting objects. They're where mathematics happens. So from our, as I explained in the previous lecture, from our elementary days up to the days in calculus, or when you're already studying things like applied mathematics, that's where mathematical structures is where everything happens. So they're basically buildings. Best I can think of them, there are buildings, and their structure are the rules that defines their operations. That's the best I can. That's how the best I can make it intuitive, at least for you guys. So that's it for this lecture, and so see you guys in the next one.